Okay, talking about 9.2 again. This time we're going to switch gears and talk about Euler's method, which is a numerical method that we use for approximating a solution to an initial value problem. So, to wit, what's the problem? We suppose we want to solve the IVP, solve y prime equals capital F of x sub x and y. What this statement really is just saying is we can write y prime as some statement involving x and y, just kind of like we do with the direction field, right? Some function of x and y, and it's going to give us the slope subject to y of x sub naught equals y sub naught. So we're given an initial value. If we cannot solve, or we prefer not to analytically solve the IVP, we use numerical methods. Pretend that says numerical. Unfortunately, the method that we're going to talk about here is not very powerful, but the idea is actually pretty cool. So let me just sketch briefly what we're talking about, right? Euler's method. And this is connected to what we discussed already about direction fields. So really what we're talking about here is we're kind of going to take the direction field as our guide to figuring out what the solution curve should look like, right? So just as an example, let's just suppose that we start at some x naught and some y naught. And although we may not, we will not know this, we know, or there is some solution, right, passing through. So this is the actual solution curve, right? But we also have the direction field segment, right? Which is a tangent line, right? So the slope is given by y prime of x sub naught, y sub naught, right? So we're plugging it into that function f, right? And that gives us the slope of the solution curve at that point. Now, what we're going to do here to figure out another point on that we suppose is on the solution curve, right? We imagine we're extending this direction field line segment through a step size of h. So we're adding a tiny increment to x sub naught. So that distance is h. I guess I drew the point at the wrong location. So the actual y1, right, or the actual y value at x sub naught plus h is not exactly the approximated y sub 1. And the y sub 1 is approximated by extending this slope, right? So we're basically just adding a tiny amount using the slope and how far we go. So imagine that this is really kind of thinking about a linear approximation to the curve and then getting the other endpoint's y value as our approximation, okay? So this process, though, is iterative, which means we repeat this several times. So given a small, we hope, step size h, we find the successive approximations. So we're gonna get what we call a mesh of y values that approximate the function, and so we can use those to extrapolate a curve that approximates. So basically, if we're thinking about what that ends up looking like, it will differ slightly, but it'll be close enough if we get a really small step size. So given our initial value, right, x sub naught, we get our y sub naught, which is given, right? And then at the next x value, so we add some h, we get a new y1, which is y naught plus h times f of x sub naught y sub naught. Okay, so here's how to think about this. So h times f of x sub naught y sub naught is h times the slope. So we're getting like this amount here. So, and this is the slope at the 0th point. And similarly, if we extrapolate further, right? So x sub 2 is going to be x sub 1 plus h, so we move out further again by another step size. And we get y sub 2 equals y sub 1 plus h times f of x sub 1 y sub 1. So we're building on the previous function values that we obtain. Notice that we have to use in y sub 2 y1, right? And that's going to give us the slope at the first point. And in general, given some previous point, so some previous node x sub n minus 1, we're going to add h to get the new x sub n, and y sub n is going to be the previous y value plus the step size times f evaluated at the previous mesh point. So that's Euler's method. This is Euler's method right here. All right, so how do we put this into action, right? We're going to do an example, okay? The method is simple, okay? But error propagates pretty quickly because we keep using approximated values to build the next approximated value. So let's see an example. We're going to use Euler's method with step size 0.5 to approximate y of 3 given the dE y prime equals y minus 2x and subject to y1 equals 0. Okay, so our initial value problem gives us x naught equals 1, and y naught equals 0. Okay, so we're given an initial point, right? And we're going to use that and the slope. So this is our f of x sub y to determine the next mesh point. All right, so how do we want to organize this? So we have the initial point, we have the function that we're going to use to evaluate to find the new slope. And we also have, I'll clarify, that means h equals 0.5, okay? So how we want to organize this, so we're going to have our nodes x sub I, okay? We're going to have our approximated slope f of x sub I minus 1, y sub I minus 1. And we have the approximated y value I, okay, which remember is going to give us, is given by the previous one plus h times f of x sub I minus 1, y sub I minus 1. Okay, so we're going to start by setting up the so this is going to give us 3 columns. And we start at the initial x sub naught equals 1, x sub 1 equals 1.5, x sub 2 equals 2, x sub 3 equals 2.5, and finally x sub 4 equals 3. So we're going up by 0.5 each time, right? Now the slope at first, right, our f of x sub naught, y sub naught, we can plug that in directly. We're going to plug in our initial value. So 0 minus 2 times 1 equals -2, okay? And then we're going to find our y sub 1. Actually, y sub 0 is already given. So that we don't need to worry about. We already have that. But in order to find the next approximated slope, we need y sub 1 first. Okay? So it feels counterintuitive to go back. So really we need y sub naught. Let me illustrate the flow of information here. We need y sub naught to find the slope of x sub naught, y sub naught, right? So the first direction field segment. Then we need that to find the next y value. So remember, that's going to be 0 to the previous y value plus 0.5 times the previous slope, -2, okay? And that's going to give us -1. Very nice. And now we use that to find the next slope value, f of x sub 1, y sub 1. Y sub 1 is -1 minus 2 times 1.5. Okay. 2 times 1.5 is 3. -1 minus 3 is -4. Okay. We're going to use that now to find the next y value. Y sub 2 is now y sub 1 plus the step size times the previous slope, -4. Okay. So then, now we get equals -4 times 0.5 is going to give us -2 plus -1 is -3. Use that now to find the slope at x sub 2, y sub 2. So again, that's going to be y sub 2, -3, minus 2 times x sub 2, which is 2. And that gives us -3 minus 4 is -7. Use that, again, to get y of 3. Y sub 3 is y sub 2, -3, plus 0.5 times the previous slope, -7. Okay, so -3 minus, let's see, what is that? 0.5 times -7 is -3.5. So y sub 3 is -0.25. No, -0.5, sorry. Then we're going to use that to find the next slope value. F of x sub 3, y sub 3 is -0.5 minus 2 times 2.5. 2 times 2.5 is 5. -0.5 minus 5 is -5.5. And now, the last y value that we want, y sub 4, which is the y value at 3, is going to be the previous y value, Yeah, reset. It doesn't matter. I like the colors that they preset for me anyway. Negative 0.5 plus 0.5 times negative 5.5, okay? And 0.5 times negative 5.5 is negative 2.75. So negative 0.5 minus 2.75, which is negative 3.25. Then and we should be careful to say approximately, right? Because it's not really the function value or the y value of 3, but it is close to it. So remember, that's going to be negative 3.25. And that's it. Okay, so our conclusions here, though, we get an approximation to the unique solution. So under the right conditions, typically some statement about the continuity of this f of x of y over some region of the xy plane. We're not going to talk about that in any detail right now because we're not ready to talk about it. An IVP has a unique solution, y equals little f of x, right? And so we get y sub I is approximately this f of x sub I in the form of a mesh, right? And as we take tinier and tinier step sizes, each y sub I is going to approach the actual function value, regardless of which I we're talking about, right? So we can go out as far as we can, as far as we want, right? Maybe we find y10, right? So we're going to repeat that iterative process, but if we take a small enough step size, it should be approximately y, even if the convergence is slow. So it may take a long time. We may have to find a very, very, very tiny step size in order to make this close enough. The Runge-Kutta methods improve on this. In fact, all the numerical DE solvers that you'll find on the internet, on your calculator, etc., are going to be at least as good as the Runge-Kutta methods. But here, this is the only one that we really are going to talk about in any considerable detail. If you are interested in this, you are welcome to take, I don't know if, it's not all the time. Sometimes for the sake of, in the interest of time, these topics may be skipped sometimes in Math 420, but you would definitely see them in a higher math course called numerical analysis. So that's it. That's all we're going to talk about for Euler's method. We're going to move on to the next section in the next video and talk about separable equations, where we finally have a method for analytically solving a differential equation.